John here. Let's talk about interfacing a Model 15 Teletype to the Z80 Retro board. In a corner of the basement, hiding under a tarp for the last few decades, has sat this particular Teletype machine. Apparently, this one was manufactured in Chicago. Now, according to Wikipedia, and to the best of my own recollection, in 1988, when I briefly worked for what was then Western Electric, which was at that same time merged with Teletype Corporation and other AT&T entities. The Teletype Corporation was headquartered at 5555 West Huey Avenue in Skokie, Illinois. Today, it's the home of the Village Crossing Mall. If you visit that mall today, the closest thing to the Teletype address is this particular space right here at 5553. Teletype was no small company. There were other buildings around the area as well. And since my particular machine definitely says Chicago on it and not Skokie, it might have been born on the corner of Wrightwood and Southport. I'm sure that I'm not the only one that finds a little bit of humor in the fact that the street number is 2600. Google it. Today, this particular building is condominiums. One of the owners was nice enough to let me look around in the lobby, which includes this particular picture of the building, which suggests that they've done a very good job at keeping faithful to its original form. I find it a little bit interesting to think that this particular machine has found its way back here, not far from where it most likely began. Now, first things first here, my printer is a little different than the ones I've seen demonstrated on the various interwebs. Mine has a box on the right clearly marked 50 baud. So I have reason to believe this one runs at 50 bits per second. Most of them that were used in the United States run at 45.5. So, first clue, this one may not have been used primarily in the US. Or maybe Canada. I don't know. Did Canada run at 50? Let me know in the comments below. Somebody probably recognizes the vintage of this thing. If it is at 50, where the heck was it? Let's start with how the keyboard generates the serial data and watch how that then is interpreted by the printing device before we dive in and try and figure out how to connect it to the retro board. If you want to send characters using the keyboard, what happens is, of course, you use the keys, all right? So we have an auto repeat on the space bar, and that is because when you hit the space bar, it pulls on this lever here, and when this is pulled forward, this thing continues to send character codes, okay? Here's the carriage return and the space. So let's look a little bit more closely at what happens when we are hitting these keys. Like here's a carriage return. You can clearly see that there's a lever that's released over here on a cam lobe. And every time that thing goes down, it's the beginning of a character. Now if you watch these little levers in here, as I hit different character codes, I don't know how well this will show up on the video here. Let me send some different codes. I guess you can sort of see it happening. What's happening is these little levers here go this way for every time there's a 1 bit in this 5-bit position in here. You gotta hit various letters and spaces on the keyboard. So what's really happening then is the reads in these on these leaf switches here are opening and closing depending on whether or not these hooks let them do so at their associated time while this camshaft rolls around. And there's a lobe for each one of these bit positions. Now, which one of these levers allows the read to open versus not open is dependent on the linkage that connects the keys. These little levers here, underneath here, will hook or unhook these little grabber thingies on these leaf switches here. So the transmission bit rate then is dependent on this camshaft in here, while all the lobes cycle by at different rotational angles as the shaft rotates to allow each of these levers here to be unhooked at their associated appropriate time. Now there's some cables and stuff that leave the teletype here. We've got these these two black ones. This is the 110 volt AC wall power, and these two leads here go to 1/4-inch jacks. The red one connects up to the keyboard from this shaft here, and the black one goes to a coil on this side over here that taps out over the course of time the bits that have arrived. And what these coils do is they pull on a lever here that's hooked up to this this thing right here. Now this piece of metal here, which is hooked up to the coil, you know, this lever goes up and down. What happens is these little fingers here can feel whether this metal bar is up or down at any given point in time. Now I got to be careful. If you got one of these, don't poke your finger on in there unless you really know what's going on. Because if you get too close, your finger will get caught in the clutch of this and tear it up, and you'll get kind of injured pretty bad. So anyway, watch what happens. If I push this down as if that coil was de-energized, you'll see a metal finger whip around really fast here, which is released by the clutch in this shaft when this thing first goes down. When that thing comes around like this, again, there's a set of cams that allow each of these fingers one at a time to reach up and feel whether this bar is up or down to decide whether or not we're dealing with a binary 1-bit or a 0-bit. So let me just push it down by hand, and you can see the clutch is releasing that metal finger. You see it spinning around right in this area here. That's where you don't want your hand. It would hurt very much. Now, by happenstance here, when I released it, you can see one of the fingers is up and the other ones are back, okay? Let me hit a couple of keys here. And you can see what we have there is a 100% mechanical U-arch, okay? Now, which fingers here are forward and backward depend on the timing of when this is up and when it's down. And it goes up and down at 45.5 to 50 bits per second. Now, a lot of these printers were designed to run 45.5 bits per second, but I suspect mine is designed to run at 50 because it simply says so right over there. Okay, so at 50 times a second, give or take, and I mean, even if it ran at 45.5, the difference is 1 millisecond out of 20, roughly speaking, in terms of timing, spread out over the course of 5-bit periods, which is not enough to really make any huge problems. I run this printer at 50 bits per second and it works fine. When I run it at 45.5, it doesn't work fine. So I'm pretty sure it's 50. So anyway, as you can see, these fingers here are hooked to these levers there, and depending on which key I hit, you can see these levels are going forward and backwards depending on which fingers are up and down. Which one of these goes forward and backward are hooked up to some levers underneath here, which I don't know if you can see so well at that angle. Let me see over here. I'm running around with my phone here. Oh, that's a much better angle. So you can see which ones are up and down, and you can see that it's grabbing a finger, kind of a hand that grabs these. That one's up right now, and now it's going to go back down if I hit some other keys, okay? Now, it must have been the carriage return key. Now, which one of those goes up and down controls these things here. I believe they're called vanes. And you can see which ones go up and down here. Those are your ones and zeros again. And those control these levers over here, which ones go left, or rather up and down, and left and right. Will depend on which keys are pressed. And depending on which one of these goes up and down, and you can see the lever action going back and forth like this, what they're really doing is they're moving these stacked set of metal things back and forth. And if I come down here, you can see that there's a bunch of holes in there. Each one of them has a different set of holes, or notches, I should say, at different positions, and they're all of different widths. And depending on how you line these stack of metal pieces up, which ones are, in this case, on the right and on the left, that's your binary code again, the Baudot code. We'll choose which one of these keys will be able to print. And the one that prints, as you can see, that one's kind of getting pulled back every time it prints. What happens is, right in here, that knot, these set of notches happen to open up just right so that this key can fall down into the hole that has been made in there. I don't know how well you can see that here. I think we can see it pretty good. All right, this is the only key that has this open notch because of the way the encoding is on all these metal pieces. as they move back and forth, one and only one can have a hole that opens up. When this key here falls down into that hole, what happens is there's a little hook on the bottom of the key. That hook right there will, when it does not fall down, it's held up in the position it's in right now. Let me see if I can get one of them on the end over there to print. What is that last key? Last key has, what is that on there? It looks like a Z, actually. So if I hit the Z key, what you'll do, you'll be able to see it fall down into the notch. All right, you can clearly see that one's being pulled back, but none of the other ones are. Right now, when I hit the Z, you see this bar that's hooked up to this thingy here that slides back and forth this way, and there's a rounded bar inside. And there, it comes back and it hooks that that finger that's sticking out on the bottom of that key. When that happens, and the key, this is pulled out towards me, there's a lever inside there, and you can clearly see that when this is pulled back, the key goes up, bang, and it goes up and hits the ribbon and prints something. Now, where things like carriage return and the non-printing characters are concerned, there's this set of levers and fingers inside here. I don't know how well that's visible in there, or how easy it is to read the various writing on this metal plate down here. What happens is, if any of these sets of fingers inside here are allowed to move in this direction, come forward, based on whether or not they hit the back side of all these veins, okay, then the linkage is triggered for whatever those other non-printing characters are supposed to do, like the carriage return and the line feed and ringing of the bell and the shifting into letters and figures modes. So in the simplest of terms, the keyboard interface basically works like this. What we have are the red lead that comes in off of the printer, or the Teletype, okay? We'll have two wires in it, and those wires come in here like this, and they go to what is wired in series, those leaf switches that you saw in there. There's going to be 6 total. 4, 5, 6, like this, okay? The first one here is going to be the start bit. And that was the one that was most obvious when you saw it running. When this thing would open up for the duration that it's open, that would represent the start bit of the 5-bit Baudo code. So we would then have bit, what comes after that, right? Bit 0, 1, 2, 3, and 4. And each one of these things has a chance to open based on a cam that's spinning around in there that always opens the start bit, but optionally opens up any one of these additional 5 bits depending on which key was pressed, okay? And the output of this, again, this is somewhat simplified. This is the schematic, period, all right? And I say simplified because it's obvious that there's a capacitor and an inductor of some kind in this circuit in some capacity, most likely providing a snubber. I say logic, but you know, some sort of a passive snubber circuit to deal with the flyback voltage that can come back off an inductive load, which is what the coil really represents on the other end of where this will ultimately connect, okay? Now the printer is even easier. It looks like this. The black lead that comes off the side of the device comes in like this, and there's a big old coil, and that's that. Okay, so this coil here, right, is going to have an iron core, and this is what controls that mechanical device that kind of looks like, I'm going to have to draw an ortho view of the thing like this right here, and there's another one it's hard to see that's on the other side like that, and there's a bolt in here, and this kind of reaches up on that arm, and when this coil goes on and off, these fingers slide up and down. Here's a closer view of the actual mechanism. So this is the thing that's kind of going up and down like this, and what again is hard to see unless we actually dismantle the printer. The metal pieces of those various fingers on the top actually have a full C shape like this, okay? So when the thing is up like this part here hits this bottom metal piece, and the top one is free to fall in like that. When it goes down like this, the top one can't move. It hits this top metal bar, and the bottom one slips in here. So this is kind of on a pivot here, and it will kind of go back and forth like this, depending on whether this is up or down at the point in time where this is another camshaft in here is allowing each one of these independently of the 5 that are in here, right? Because there's a whole stack of those things, 3, 4, and so on. Each one of them has a different point in time where it can move forward and either kind of fall down here or up like that, okay? This thing then has this little a ball that reaches the back here, and there's a little metal thing that kind of grabs like this, and it causes these vanes here to either flip one way or the other way, all right? So electrically, really all there is a simple coil that has to be on and off over the course of time, just like it is in a regular old UART. I mean, this is a UART, which would look like this. There'd be a start bit here, and then there would be bit number 0 during each one of these specific points in time. Bit 1, 2, 3, and 4, because this is a 5-bit Baudot code. And I believe officially there's supposed to be 1.5 stop bits in here, but I have found that I extend this, okay? Probably because I'm running it at 50 baud, and maybe it really should be at 45, and I don't really know. Again, I would love to hear from anybody that knows about the vintages of these Type 15, Model 15 type of machines, because, like I said, mine works better in one way and as opposed to the other. It also has this mark right on the side, 50, right? But when I run it at 50, what I do is I make this 2.5 bit times instead of 1.5. So this is, let's call this John's basement protocol. All right, because mine doesn't like to work any other way. Okay, so here's your start bit. Okay, and so on. Now, each one of these bit times for me is going to be 20 milliseconds. Now, if you run it at 45.5 bits per second, what you end up doing is the duration of this thing is really more like 21.9 milliseconds. All right, so about, I guess maybe 2 milliseconds off. I think I said 1 millisecond earlier. It's really 2, which is what? Going to be a 10% error. Now you stretch that 10% over these many. Actually, the only number of bits you really care about are these, because you can have as long a stop bit as you want. In fact, during the stop bit, it has to be high. So the way I drew it is a little off. You don't have an option. You must go high here and stay high for the stop bit. Bit Z. In this case, normally any modern system, you have 1 stop bit, and these older ones needed 1.5 to, in my case, 2.5. Anyway, so we're looking at 2 milliseconds of error times 5. So you end up with potentially, I could be off by, a 1/2 bit width by the time I'm done. And that actually is not a huge problem. Apparently mine works very well at that particular speed. So this particular coil is not going to operate at RS-232 voltage levels. Definitely won't operate at TTL. This is what we call a 60 milliamp current loop. All right, so what we need to do is generate 60 milliamps of current. We need to set it to whatever voltage is necessary for this to be true. Now, the reason they did it using current instead of voltage is because, remember, this cable here could be miles long. These were used, in the battlefront of World War II. They were used all over the country, and I mean, this had to work. Okay, so it turns out what you would do is you'd have an arbitrarily long wire pair running a coil far away, and you'd put a little current loop meter on here, regular old ammeter, and you'd ramp up the voltage until the thing was drawing 60 milliamps. At which point in time you knew there was enough current flowing through this coil to pull down the metal finger here, so that you could be operating this this pair of bars to tap out the code on the far end. It really was as simple as that. So I need a circuit that'll generate some voltage suitable for 60 milliamps to flow through this coil, and I need to be able to turn it on and off at 20 millisecond intervals in here in order to emit any bit pattern that I want. Now, for simplicity's sake, the retro board outputs RS-232. So if we take 232 from the retro board, and I'm only going to hook up the printer. I don't need the keyboard connected to my retro board. I'll leave that as extra credit. You want to do one of those, record it, post a video. I'd love to link to it. I'll add it to my playlist. Let me know. Anyway, what you have here is kind of a wide range of voltages, really. It could be anywhere from 5 to like 17 volts on the transmit line, right? And then you have the ground line here. I'm going to bring that in, and I'm going to just connect it to my local circuit ground here. And the transmit signal from the retro board, what I'm going to do is I'm going to rectify it like this. Then I'm going to put it through a 1K ohm resistor, nominally close enough, right? And then I'm going to hook it up to a transistor like this, an NPN. Ground the emitter. The collector is just going to go right over to here and through another coil. And then I'm going to go to 5 volts. And over here, I'm going to put a flyback protection diode like so. This is going to be the coil of a simple relay, which is an RKT-5 relay, and I Googled it. You can still buy these today. This is the relay. I know it is because I recognized it when I dug through my junk box and found it in there. This is probably the same relay, certainly the same model, that I used, 40 years ago, the first time I ran this particular machine from my homemade computer. No, I almost never throw away any kind of old electronics parts if there's any chance that they might ever be used again. So as you can see in this drawer are a bunch of RKT-5 relays. These have been here at least 40 years. And I know this because this little metal box of drawers, you can tell by the yellowing tape, was given to me by my father when I was in grade school, specifically to hold old electronics parts. You never know. In, a couple of decades, you might decide to build a retro project. These were new when I put them in here. Okay, so this relay is a double pole, double throw relay. And what I'm going to do is take the normally closed, or one of the normally closed poles, all right? And I am going to take that and put it in series with the current source and use it in lieu of this. So what I'm going to do is I'm going to unplug the red lead off my printer. So this is the red lead. Okay. It's built like that. Anyway, and then I'm going to plug this in instead. So this one is going to be my substitute for the red lead. And ultimately, with this in place of the red lead, what's going to happen is I'm going to take my 60 milliamps from the power supply that the printer came with anyway. I'm going to run that out. I'm going to go through this circuit here, right? So it's going to go through my my interface. Okay. Then it's going to go through the coil in the teletype, back like so. Now it turns out that the 60 milliamp power supply that actually comes with the Teletype is probably also 80 years old. And this is around 110 volts DC. Now, I don't want to be anywhere near this thing, especially since it uses something I don't even recognize, which are copper oxide rectifiers. I'll show you a couple of close-up pictures inside the power supply in a minute. It still works, obviously, and I'm going to just go ahead and use it. But I'm also going to plug it into a full isolation transformer in my shop with a floating neutral. So this thing is very much isolated. I don't want to feel 110 volts if I bump the wrong thing. But this is essentially the whole circuit, right? So this is the Teletype coil here. And this is going to be my, this is going to be this relay right here. This is the RKT5. KT. Well, it's hard for me to write and talk at the same time, right? Okay, and then I'm going to just hook this relay up to my 232. I'm going to set my retro board to run at 50 baud, and this little relay will chatter on and off very quickly, but it'll do its job, and all should be well. Now, when I'm running this thing in my shop area, it generates this the flyback voltage on this coil is obviously enormous, and it causes every USB device that's plugged into my machine, which is probably 8 feet away from the Teletype, to continuously appear as if it's being unplugged and plugged back in. So the bitrate error on the USB interface is enormous. So what I'm going to do is put a snubber capacitor in here, which pretty much eliminates that in my shop. And I'm going to put in a 1000 puff, like 2 kV capacitor in there for this thing, right? And in fact, this is the kind of capacitor that you would find that connected up to any Ethernet interface on the center taps of all of the differential pairs that come in on a 10 base T or 100 base T or gig, the various standard Ethernets. And this is a very common thing on there. Why? Because I have a bunch of these around from an old project that you had Ethernet interfaces on them, and the only ones I have that have high voltage. So I threw that on there. It helps enormously. I suspect if you look around on the internet, other people that have been building these interfaces use back-to-back Zener diodes that are at like 100 volts or 120 volts or 200 volts or something like that. Anyway, I don't have any of those in stock, so I'm going to just do this and call it even. It works well enough. I'm sure there's all kinds of harmful interference coming off of this. If somebody wanted to listen to an AM radio within 100 yards of my home, they're probably hearing this thing chatter like crazy, especially when I don't have that snubber in there. In any event, this is what I've got. This is what I built in, my high school days, like my senior year, I think, is when I was dabbling around with the old Explorer 85. That unfortunately I managed to break because it didn't have a case, and I think I was cutting a piece of wire or something, and a little metal flick flew through the air and then landed on the circuit board, at which point it never ran again. So, lesson learned. All my computers now have cases. You keep them closed or well protected, or cover them up or power them off if you're working in the near vicinity. So where do we get our 60 milliamps at 120 volts? We get it from this, I'm going to go with a surplus prop from an old Frankenstein movie. Yeah, so this is what we call a copper oxide rectifier from Western Electric, which was absorbed into Bell Labs during the AT&T divestiture, which is then evolved into Lucent Technologies, for those of you that are a wee bit on the younger side and might not have recalled. So anyway, this is a power supply, which we're going to see is a bridge rectifier in it, an isolation transformer, and a simple little filter that can generate 120 volts DC at 0.125 amps. It's 125 milliamps, which is more than enough to run our 60 milliamp current loop. And yes, I'm going to go ahead and use the same power supply because I don't have any other one around to do the job. And it works. Why not? So here's what that thing looks like if you take the lid off and have a look-see inside. These are, things looks like a bolt with a bunch of washers on it. These are copper oxide rectifiers. There's 4 of them. Clearly that's a bridge rectifier. This thing over here is the power transformer. It's going to be a 1-to-1 isolation transformer. It's got a couple of taps over here, most probably to deal with 110 volts versus 120 volts or whatever. So you can change the output voltage accordingly. This over here, I believe, is a choke, and this over here is a capacitor that they use to filter the output a little bit. This button up here disconnects the line power if the cover is off, because otherwise you got naked 110 volts off the wall all over inside here. Okay, now I'm pretty sure this is just an isolation transformer in here. So that you're not dealing with 110 volts AC rectified to DC, as it is with neutral and ground earth referenced outputs coming out of here, and people would be dying all over the place if that were the case. Now, I don't trust this thing as far as I can throw it. Oh, you can see the corner in the upper left corner here is the back of an isolation transformer that I have around the shop, a 1-to-1. With this over here is a tag I put on the back to remind myself that it is a floating neutral. So this is, we have an earth ground on the third prong terminal. These other 2 terminals are 110 volts AC at 60 hertz, and neither of them has any reference to earth ground. In other words, I can touch either one of these if I want to, and I will feel not a thing. I'm sure this will do the same thing, but given its vintage, I'm going to go ahead and throw mine in there for double measure. Now, if we flip over the cover that I unscrewed from the top, we see they included a nice schematic diagram of what's in there. If we zoom in a little bit, these are the 4 diodes, obviously wired in a bridge rectifier form. This is the isolation transformer right here. The primary comes in, and you can pick, obviously, whatever voltage you want coming out of it using the screw terminals on this block here. This here represents the line cord you plug into the wall. This is the door switch that disconnects the power if you have the lid off. Over here is the output cable, and here's the capacitor over here that does the menial filtering. Okay, so that's what we're looking at in the box. This here is going to be your choke, most likely a choke coil, the way it's in this circuit. All right, so this is what that box has in it. Now, when I received this, other parts I got with it included this nice block here, which came with a fuse and this high watt 2K ohm resistor here. And a nice milliamp meter that somebody marked a little red notch right there of what the amount of current is supposed to be when the system is idle. So let's add a smidge of detail to our drawing, right? So we have our 120 volt DC supply here, right? We go through this 2K resistor. Then we have our meter here. Then we have my relay. And then we have the coil that's inside the printer, like this, with the snubber capacitor here. Okay, volt 1000 off there, right? So let's have a look-see at how this is connected to the retro board. First of all, I got auxiliary jack B over here. I jumper the RS-232 like this, so the transmit line is connected to pin 2. Pin 2 is right here, so I'm going to tap off that, and this is the ground. So this I'm going to take the RS-232 from the retro board. If we move up to the stratospheric view of the board, note also where these jumpers are up here. I'm running the CTC into the SIO. It is, in other words, the SIO is not directly clocked by the bitrate oscillator over here, okay? All right, so here's a close-up view then of the circuit that we just drew up, showing how I'm going to hook up the RS-232, which comes in right here. This is a transmit line from the retro board through the diode, the 1K resistor. The NPN transistor here is a 2N4401, because that's what I had on hand. What am I doing here? This here is the emitter, so that comes up and around here to ground. This lead is you could barely make out the black right there, which is the ground line going over to the retro board. This header here is where I put my power supply. I run this on a 5-volt supply from my bench supply because I don't have a handy way to steal 5 volts off of the retro board. I suppose now that I've just said that, I could steal it off the connector header for the SparkFun SD card. That'd be another way to get it. Nonetheless, what I did is I just put a gator clip here, and I gator clipped the other one on over here for the 5 volts to supply the voltage to trigger this relay over here. Okay, so there's my transistor. The output of the transistor, the collector, comes up here and around and plugs in right here. There's the flyback diode for the RKT5 relay. Changing the angle of the shot a little bit here, you can see clearly there's the RKT and so on. The leads on this thing were not long enough to stick all the way through and into this breadboard, so I stuck it into a incorrectly fitted wire wrap socket that I had lying around in order to get the thing to stay in the board. It barely kind of worked, but it kept popping out of the board while it was being used. Very annoying. So these two leads here are the go over to where the red lead would normally go on the Teletype machine, all right? So this is your 60 milliamp current loop flows through these leads here. Now, you don't see this number capacitor over here because it wouldn't be as useful to put on this end of the circuit. It's actually clipped onto the other end of these leads over by the Teletype. And thus we have a description of the machine, its interface, and the timing that we need to transmit the 5-bit Baudot code from the retro board to our Teletype. So next time we'll look at the software on the retro board and how we're going to convert 7-bit ASCII to 5-bit Baudot, and how we have to deal with a couple of timing issues that you normally don't have to deal with in the modern era with respect to what happens when you print a carriage return, for example. Thanks for watching. I'll see you next time.